Hello Paul and the most excellent community of developers with interest in programming in Python related to the Arduino environment. So this is related to a challenge of episode 14 here, which was modeling a moving marble in a room using parameters. So despite the fact that the approach was very interesting with functions and parameters, I said to myself that it would be interesting to have an object-oriented approach for this, yes, once again, because we can see how it can bring more expressive approach of the problem. Okay, so what we do here is that I will create a room, and the room will be a class. Okay, and this room will be composed of walls. Because a wall has always common properties like width 8, thickness, etc. Okay. We will have 4 walls, and we will have also 2 floors. Floor being the term here, generic term for either ceiling or floor. So it's a generic term for horizontal separation. Okay, floor will also have width 8, thickness, and of course position, etc. And we will have a wall with a radius, and of course position, like for the wall and the floor we have position too. And we will implement methods that will be able that will have the calculation to see if our ball is within the room or not. It's important because when we have our room in 3D like this, of course, we saw that when we have a move on the x axis like this, when we reach the right limit we have to reverse the movement to go all the other way around, okay, till we reach the left limit here, and then we have to bounce once again in the other direction. So there will be a method too to toggle the direction of the movement. And of course all this will be easier if we make a generalization of all those principles. So that's why I propose to do here. Now let's see the code here. You will of course recognize some of the approaches functions that Paul showed us. Nothing very new here, it's just an organization that is different. Okay, let's take this. Okay. Of course we import vPython. We'll come to the ball later. First of all, we will have a look at the class wall that represents a wall. A wall is defined by a width, a height, depth, position, x and z, thickness, and the rest is just for making it beautiful. So this is a first approach to be quite close from the functions that we saw earlier with Paul solution. I can say that later when I have some time I will have another approach, because here with this approach we twist a little bit those notions of what is the depth, what is the width or the thickness. It depends on what wall we are talking about. But in my opinion it could be more interesting to have always the same definition of the same parameters. A wall should be defined only by a height, a length and a width. But I understand that on the first approach it's easier to make it like this. Okay, so the thickness, width, depth here, position, x and z. We keep the same letters as in the vPython reference shells. Color, opacity, texture to make it beautiful. And then yes, we have here properties that will hold the limits of this wall. Okay, it means that when here, if we have a look here, when you have a wall here, okay, let's say this is the right wall, okay. This is the left limit of the right wall, this is the right limit. But this will be the same whatever the wall is. If it's a left wall, the left wall will also have a right limit or a left limit. Okay. We also have here a front limit, which I call this, and a back limit. Okay, in my room, this is the front, this is the back. Okay, left, right, top, a bottom. Those are my conventions here. Okay, and here, once for all, for one wall I can get automatically the left limit, right limit, etc., because it will always be computed the same way. For instance, for the left limit we use the x position minus half the thickness. Okay. If we see here, this is the X position, this is the thickness here, so X minus half the thickness gives us the left limit, and that's how we get those different values here. Okay. Left limit, right limit, front limit, back limit. And on the instantiation of the wall, we will directly draw the corresponding wall with the different values. Okay, this is for one wall. How to build a room with those walls? When I build a room, as we saw, I get the same values here. 12 for the width, 10 for the height, and 16 for the depth. Depth being the difference between front and back. Wall thickness is 0.5 here. Okay, so one room is composed of 4 walls, left wall, right wall, etc. And for each wall I build an instance with the corresponding parameters here. So I got my 4 walls. Okay. Same principle for the horizontal structures, separators, which I call here floor and sail, and that will be a instance of floor. It's a little bit like a wall here. Same principle. Okay. When I will have to bounce my ball, when I displace my ball, when I move my ball here, I will be interested in knowing what is here the inner side, inner dimension of my room, because of course the ball will bounce on those inner dimensions here. Okay, so I need, of course, the different limits of each wall to compute those values. That's why in the room, once I have put my different walls here, I can compute the inner values, the inner limits, which I call inner x on the right, inner x on the left. Could have called that inner x max and inner x min, but right and left is quite readable here. Okay, so for instance, the inner x right will be the right limit inside the box, and it will be given by the left limit of the right wall. If we take back our sketch here, and if this is the right wall, what we want to know is this limit. So we have to use the left limit of the right wall to know the inner limit of our room on the right side. Okay, does it make sense? I hope it does. If not, you are free to rewind and hear it again at slow speed, of course. That's the beauty of a video. Okay, same for the left side. Of course, for the left side we use the right limit of the left wall, and the same principle here for the height, and what I call here the depth of field, which is the delta between back and front. Okay, so I have all useful information given by this classroom. Now I have to define is my ball here. Okay, so the ball is represents our marble or ball here, which will be instantiated with a radius, of course, a color if you want. Most important is the radius, of course, because the radius will enable us to compute the distance between a wall and the ball, which should be position minus or plus the radius, of course. So we have the position of the ball. We can instantiate here a sphere with these components, the radius here, and we have a starting direction here, which is positive. What I call the direction is a factor that will be +1 or -1, which will be the conventional positive progression, and minus for the negative progression. So when direction is positive, we go right. When it's negative, we go left. Okay, that's a convention here. As for the, just as we did for the room, we can compute here some kind of bounding box for the ball, because the ball is spherical, of course, by nature. But we have to know here the right limit, left limit. The right limit of the ball will be its extreme limit on the right, which will be this position plus the radius. And on the left, of course, here, x position minus the radius. Okay, same for the top limit, bottom limit, etc. Okay, to make the code easier to read, implement, and understand later, I implemented some methods here. A method that will tell us if the current ball, we are inside the ball here, I remind you, we are inside the ball. Are we too much right from the container? Okay, the container here will be an instance of the room. So if we want to know if we are too much on the right, we can test here if the right limit of the ball, if our right limit is greater than the inner x right of the container being here the room. Okay, it's easier to make functions that will make easy and simple tests and then combine those different methods, in my opinion. Okay, idem for is too much left. Is it too much left in the container? Comparing the left limit of the ball with the inner x left of the container. Too high, too low, too far in. I mean too far is behind the back wall, or too close, in front of the front wall. Okay, so each one of these functions is related to the position of the ball, related to the limits of the container. So if you want to test if we are in the range of a lowered x, a lowered horizontal displacement position, are we in x of the container? Can test here that we are not too much left of the container, or that we are not too much right of the container. Okay. So if none of this condition, none of this function returns true, we will be in the allowed range of x. Same principle for the y-axis and the z-axis. Okay, as we said before, we'll have to toggle the direction will being initialized with +1. We have to toggle the direction for each of the displacement axis, x, y, z. How to toggle? If we want to toggle between +1 and -1, just have to multiply by -1 the current direction. Okay, minus by minus gives plus. Plus by minus gives minus. It's beautiful. So, how do we move with this? We have functions here to move on each one of the axes. We will move by a delta value. This value will be multiplied by the direction being -1 +1. Okay, this is for moving on x axis. Y axis is almost the same. It's the same, of course. Same principle here. So it may look a little bit verbose, but as I said, this will make it easier to express what we want to do afterwards. For instance, here, when we want to apply a movement, we want to move, but in the limits of a container, I call this method move inside. It takes as argument a delta and a container. We want to move a certain amount of distance, but inside the bounds of the container. So just for rotating the ball on itself, so we make some animation here, nothing to do with the main goal. Okay, so main goal is this. This is the kernel of our displacement movement. So obviously we want to move by a certain amount of distance, but only if we are still in the bounds of the container. So if we are in the allowed range of x values, we're not too much on the left and we are not too much on the right, then we can move on the x axis, and we move by a x value. If not, it means that we are too far on the left or too far on the right. We don't care on what side we are, because all we want to know is that if we are out of the bounds, we have to toggle the direction. Okay, we toggle the direction and then we make the move. And it's the same for y and z. Okay, once we have defined the new position, because until now we just made a logical movement, it was not a physical movement, then we can change the position of the ball with a vector using the new value of x, y, z. Okay, you see here that the delta that I use in move inside is a dictionary with keys x, y, z. So I can here define what I call a delta space here with the vector of displacement. Okay, so in my main code, once I have instantiated the room and the ball, all I have to do is to ask for moving the ball inside the room. So of course we have a lot of code in the classes, etc. Could be refactored to optimize and okay, but we make it simple here. Does it work? Does it work? So we will hold our breath and take a sip of coffee. And yes, let's try this. Okay, and here we go. It bounces, it rotates. Okay, we can go inside and watch what's happening here. Isn't it beautiful? This is my new theory of the universe. maybe Kepler and Newton will be shocked with this theory. But everything is possible with Arduino and Python. Okay, so thank you for watching, and see you soon for other adventures with the Arduino and Python. See you soon, bye.